Hey, good morning, team. Chemistry coach coming at you on another day in our um, chemical compounds journey. We've looked at ions, ionic compounds specifically, how to put them together, do formula units, different type of chemical formulas, even some organic ones. Oh, shh, don't tell anybody. We want to get into naming these babies. I sort of introduced to you how to name cations and anions, right? Cations, we don't change the name of the parent element, which can cause some problems. And anions, if it's a monatomic anion, you just take the root and add the suffix IDE. But what if we have a whole compound? What are we going to name these? And what if we don't have ions? How do we name covalent compounds or acids? And there's a whole slew of them. We're not going to name organic compounds in this class. Okay, I'll save that pain for later. Before we get into naming species, nomenclature, that's the official term, we call it nomenclature. We want to take a little side trip, put an arrow in our quiver, called oxidation numbers. Some people call them oxidation states. I use them interchangeably, doesn't matter. And what it is, it's a quantitative measure or a numerical value, because we like to compare numbers, right? 2 is bigger than 1, right? -1 versus -3, those kinds of things. We want to look at a specific atom in a specific compound or polyatomic ion, some species it's in. So maybe it's the phosphorus atom in the phosphate ion, PO4 3-. Maybe it's the titanium atom, or in this case ion, in titanium 2 sulfide or something, whatever it is, or in methane, CH4, we're looking at the carbon or the hydrogen. What's a measure of its electronic environment? So for example, carbon in CH4, it's surrounded by 4 hydrogens, right? But carbon and carbon dioxide's got 2 oxygens connected to it. Well, oxygens are more likely to pull electrons away from something than hydrogens. So that carbon in carbon dioxide is experiencing a different type of electronic environment than carbon in methane. All right? So if the oxygens are pulling electrons away, that carbon is becoming a little more positive, right? Because the oxygens are pulling electrons away. Whereas in CH4, the hydrogens aren't doing that. So the carbon won't be as positive. So we use a numerical value called oxidation numbers or oxidation states to give us an idea of what kind of electronic environment that atom's in. What are we going to use that for? Really important later on when we do redox reactions, reduction oxidation reactions, where we have a transfer, and all it is a transfer of electrons. Well, if you're transferring an electron, whatever's losing that electron is losing a negative particle, right? That's going to change its electronic environment. Whatever's gaining that electron is gaining a negative particle. That's going to dramatically change its electronic environment. How do we track that? We're going to use oxidation numbers for that. So that'll be real quick. So when we get to redox, you're going to want to review this video. It's going to help you tremendously. Because if you get these wrong, you're going to get all of the corresponding equations wrong in reduction oxidation stuff. That's not good. We're going to use it in nomenclature for a few specific species, particularly type 2 ionic compounds. So any ionic compound that has a type 2 metal. And I showed you how to do it, where we did kind of the reverse engineering, where you have a compound, you look at the anion, maybe we don't know the cation charge because it's a type 2 metal, so it could be multiple possibilities, which we can't predict from the periodic table. So we got to figure it out through the back door by knowing the anion and the fact that the compound is neutral. So we already did that using that algebra. Well, we can do that for any species, not just type 2 metals. We could do it for type 1 metals, which you don't really need to do. You can look it up on the periodic table. But we could do it for covalent compounds too, like water, methane, any kind of sugar, anything like that. We could figure out the oxidation number, the electronic environment for any atom in any species. Cool, huh? So, and later on down the road in next semester general chemistry, we may get to complex ions as well. So to name those, we have to know the oxidation number of a metal that's in there, similar to type 2 metals. All right, so this will be useful for a lot of stuff in the future. So let's spend a bit of time practicing that. Oh, bug! Oh, I missed it. Let's go through a set of rules for how to determine oxidation numbers for atoms in any species. We can say elements in any species, right? Let's have at it. There's going to be a list of them. Get ready to go. All right, I've seen many different ways to express these steps or rules or guidelines for determining the oxidation numbers for elements in a particular species or the atoms in them. So the first one, I think that I'm going to go through kind of what I look for first. I like to start with the easiest, and then I'll go a little bit harder and harder from that. So I will always look for a free element, whether it's monatomic like sodium or lead or anything like that, or diatomic or polyatomic, any polyatomic one. So all the diatomics, the chlorine, the bromine, the iodine, the hydrogen, nitrogen, oxygen, those magnificent 7, right? Or even something like P4 solid or S8 solid. It doesn't matter how many atoms are in that free element. That free element is neutral. And all of the atoms in that free element are also neutral, and they have an oxidation number of 0. So if I see an element with a solid, liquid, or gas on there, you're not going to see it with an AQ usually. Boom, I'm just, bam, that's an oxidation number of 0. Good to go. Easy peasy. Let's do the next easiest one. Let me write it up on the board there. That will be, in a similar fashion, monatomic ions. So let's put monatomic ions. For a monatomic ion, and this is where the overlap comes in, the charge of the monatomic ion is equal to its oxidation number or oxidation state. So they're not the same thing, right? An ionic charge is an oxidation number, but an oxidation number is not necessarily always an an ionic charge. So they don't necessarily go back and forth, but an ionic charge is an oxidation number of a metal cation in those scenarios. So for a monatomic ion, the oxidation number equals the ionic charge. Yay! So I look for free elements first. Say I've got a balanced chemical equation. I got to assign oxidation numbers to every element in every species. If I see a free element, boom, 0. If I see a monatomic ion, right, AQ, maybe it's dissolved in solution, and I see Na plus AQ. Well, Na plus is +1, therefore it must have an oxidation number of +1. Right? So if I have Na plus aqueous, that means its oxidation number is a +1, right? Pretty simple. Or if I see, for example, maybe an iron ion in solution, that would have an oxidation number of +3. Not too hard, right? So I started you with the easy ones, so we got the training wheels on. Now that the easy ones are done, what if we have compounds or polyatomic ions or any other species besides elements or free monatomic ions? We're going to have to think a little more because they're going to have multiple elements now. We're going to have to assign some to do that. So let me erase the board and put up some more complicated rules. All right, what if we're looking at some more complicated species? We're going to use this. This is probably the most important rule when you're assigning oxidation numbers. The sum of the oxidation numbers of all atoms in that species, all of them, you add them all together one at a time, and that total has to equal the overall charge of that species. This is going to be important. Now that applies back to free elements, right? Free elements are neutral. So the sum of all the atoms, whether it's monatomic or diatomic, must equal 0. So they must all be 0. Same with monatomic ions, right? If all I have is one atom and its charge, that's what a monatomic ion is, well, the sum of the oxidation number of the atoms, which is only one atom, must equal the overall charge, which is the ionic charge. That's pretty straightforward. But if we've got a compound, right, magnesium oxide, lithium sulfide, ammonium nitrate, something like that. Well, compounds, whether they're ionic compounds or molecular or covalent compounds, those are neutral by definition. So if I added all of the oxidation numbers of all of the atoms in it, it must equal 0. This is what we did when we were looking at how to determine the charge of a type 2 metal, which was the oxidation number of the type 2 metal. If you have a polyatomic ion or any other species that's not neutral, right? Nitrate, NO3 minus, oxalate, C2O4 2 minus, right? The sum of the oxidation numbers of all those atoms in there must equal the overall charge of that polyatomic ion. So if I take phosphate, PO4 3 minus, the phosphorus plus the 4 oxygens, oxygen 1 plus oxygen 2 plus oxygen 3 plus oxygen 4, must equal -3. This is going to help us tremendously, because what we're going to do now for the next rule is we're going to assign oxidation numbers. There's certain elements that just tend to always have the same oxidation number based on their pull for electrons when they're bonding to something else. We'll see that as the electronegativity in a second. So say we have a compound that has 3 elements in it. We're going to, 3 different ones. We're going to assign 2 of them, right? Because how could you figure out if you have 1 species and 3 unknowns? That you can't solve for that, or even 2 unknowns. You have to assign all of them except for 1. So we're going to assign the most obvious 2 if there's 3 of them, and then solve for the third. If there's 4 elements, we'll assign 3 and solve for the fourth. If there's 2 elements, we'll assign 1 and solve for the second, using this concept. This creates a chemical equation like we did when we were determining the charge of type 2 ionic metals. So number 4, we're going to assign oxidation numbers for all elements except 1. Right? So we're going to have to go through how to assign things. So we're going to assign oxidation number values to all elements or atoms, right? In any species, I don't care what it is, as long as there's 2 or more different elements in it, except for 1. And that gives us 1 equation and 1 unknown now, right? So if there's 2 you don't know, that's 1 equation, 2 unknowns. Good luck with that one, right? And we're going to solve algebraically for that. I hope I spelled algebraically correctly. Been a long time. And we're going to solve for it using this rule. The sum of the oxidation numbers of all the elements in that species, or atoms in that species, equals the overall charge. So let me show you some assigning rules. For my class, this is in your general chemistry notebook. You can, it depends on the version. I think it's page 92 or something like that. So I'm just summarizing this, and this is a handout on my website as well you can find. So let's go through the assigning rules, and then we'll just do a bunch of example problems until we fatigue out. Hey! All right, these 3 assigning rules will probably take care of you for 90 to 95% of everything you're going to run into. All right, we have one more. We're going to have a part D if you run into something that doesn't have fluorine, oxygen, or hydrogen, or you're stuck with 2 more elements that aren't one of these, and you're like, how do I deal with this? I'll give you some extra need-to-know basis rules for that one. But in general, fluorine is always going to be -1. Of course, unless it's the free element, where like F2 gas, it would be a 0, of course, because that's neutral. But fluorine bound, to another atom with a chemical bond in some compound or some kind of species will be a -1. Always, no exceptions. So fluorine's easy, but you don't see fluorine that often. Oxygen or hydrogen, you see the most, right? A lot. So oxygen, we're always going to assign a -2 oxidation number, unless it's the free element, right? So O2 gas or O3 gas, ozone. So if it's a free element and it's neutral, we're going to assign it a 0. There's also another situation where oxygen can be part of a peroxide. That's one of the polyatomic ions on our list, the O2 with a 2- charge. It's an O- atom and an O- atom chemically bonded together to give O2, O2, diatomic oxygen with a 2- charge. So in a peroxide, each oxygen is a -1. So you just got to watch out for the peroxide. That can mess you up a little bit. But in general, oxygens just go boom, -2, boom, -2. You see it in water, -2. See it in carbon dioxide, -2. You see it in glucose, -2. Boom, you're good to go. Hydrogen is pervasive. We see it all the time. It depends what it's bound to. It can either gain an electron or lose one. So when hydrogen is bound to a non-metal, like in water, H2O, or in methane, CH4, hydrogen, we're going to assign it as a +1 oxidation number. Boop, easy peasy. Less common, we'll see it bound to a metal where it's a hydride, like lithium hydride or sodium hydride or titanium hydride. There we're going to assign it a -1. But by far, the most common one's going to be a +1. So if you're stuck on a test, just go, oh, oxygen -2, oh, hydrogen +1. You're probably going to be right. But there's exceptions to it. Now, what if we run into something where we've got 2 more elements and they're not fluorine, oxygen, or hydrogen? What do we do? Oh no, 1 equation, 2 unknowns. Let me show you. I got to introduce a term called electronegativity. I'm not going to go into gory detail on electronegativity, but we're going to use it to take the 2 unknowns and then decide which one we're going to assign a value to, and then solve for the other one. So let me, find, and if you have my website, print out the electronegativity table. I'm going to show you how to use that. Be right back. All right, gang, 2 more rules for assigning. I told you there's going to be a lot. But once you get them down, hey, fluorine check, oxygen check, hydrogen check, boom, boom, boom. Another one, hopefully you figured out, that we could always assign is type 1 metals, right? Group 1A, alkali metals, they're +1. Group 2A, alkaline earth metals, are always +2. Aluminum's +3. Cadmium, zinc are +2. Right? Aluminum +3, silver +1. If you know the type 1 metals, you could always assign those. Boom, they're never an unknown. So we can assign quite a bit. Usually you're going to be good at that point, right? And there's only one element left at that point to do that. But let's look at the next one. Pull out your electronegativity table, and let's have a poke at it. Ready? Sorry, I had to pause it there. The printer went on. You gotta love working at home. It's like, wow, what's cats running everywhere? Printer's going on and off. Lawnmower's going off in the neighbor's yard. Yeah, you just gotta have fun with it, right? All right, so we've got type 1 metals down. Now, like I said, we're done most of the time. But if we run into a scenario where we've assigned oxygen, assigned hydrogen, assigned fluorine, assigned type 1 metals, if they're even there, and we're still left with 2 elements, and we're like, man, I can't assign any of those. I got one equation with 2 unknowns. What do I do? What do I do? Teacher, teacher. All right, you're going to take out your electronegativity table, and you're going to look at the remaining 2 elements and look which one has a greater electronegativity value. Electronegativity, here's your electronegativity table, so make sure I'll provide these on the exams and stuff. So these have numerical values. We're gonna introduce electronegativity later, but in general, when you have 2 atoms bond together, there's going to be a tug of war for those bonding electrons, right? They're sharing electrons, unless it's an ionic compound, but there's still electrons involved. Think of it as a tug of war. And the bigger the number, the higher the number, the more attraction that atom has, the more it pulls those electrons towards itself, and the more negative it becomes, right? So you can see, hydrogen here to 2.2. If I bound that in methane to carbon at a 2.55, carbon's got a bigger value than hydrogen. So what that means is the carbon's going to be not a lot bigger, but it's going to be pulling the electrons towards itself, becoming a little more negative. The hydrogens become a little more positive, right? So what if I end up with a sulfur with a 2.58 and an iodine with a 2.66? Pretty close, right? But the iodine's a little bit higher. So it's going to be a little more negative. So if you've got 2 elements left and you're not sure what to do, take a look at this electronegativity table. And in general, the numbers get bigger to the right and smaller going down. So fluorine, 3.98, that's the biggest of all of them. That's why it's always a -1. Oxygen's the second biggest at a 3.44. That's why it's always a -2, its preferred charge, unless it's with fluorine. Then you got some weird stuff going on. So if I'm stuck with a bromine and a nitrogen, I'll take the one that's got the larger electronegativity value and give its preferred anionic charge, which we know how to predict. It's just the number of columns away from the nearest noble gas. Notice noble gases aren't on here. Right? They don't naturally form bonds. We can do it synthetically, but they don't naturally do it. We'll assign that more electronegative one, and then that leaves us with one unknown. We'll call that X, and we'll solve for it algebraically. All right, we've got all our rules. Let's do a whole bunch of examples and apply these rules and show you once you do it enough, it becomes pretty routine and pretty easy. You guys ready? I highly recommend you pause this and tell me the oxidation number for every single one of these elements and every single one of these species, right? Some are charged, polyatomic ions, some are compounds. Doesn't really matter. We can figure this out. Try it and see if you get the same thing I do. So you're going to assign. So see, the first one has 2 elements. Assign 1, solve for the second one. This one has 3. Assign 2, solve for the third. This one has 4. Assign 3, solve for the fourth. The same thing every time. Doesn't matter how many they have. Most you could probably do it in your head, but if you're having trouble with that last one, just do it algebraically, where just the sum of the oxidation numbers of all the elements on all that species, all the atoms, right? So this one, the lithium plus the chromium plus the 4 oxygens is going to be 0. This will be 0. The sum of the 2 carbons and the 4 oxygens here will equal -2. You should be good to go. All right. Pause it, try it, and then see what you get. If I'm going to do this, I've got carbon, oxygen. No, there was no rules on assigning carbon. You're almost always going to solve for it. So, but it's oxygen. There's no fluorine. It's not a peroxide. It's not a free element. So, boom, that's going to be -2. So let's call this X, right? I don't know what X is. We're going to solve for that. Let's do our algebra. We're going to sum everything up. So we got 2 carbons, right? Everybody agree? So 2 carbons times, I don't know what its oxidation number is. Or you could go X plus X if you wanted to. We've got 4 oxygens. So let's take the number of oxygens times its oxidation number, which is -2, will equal -2. Now, I haven't done these ahead of time. Hopefully I do my basic math right. That's usually where I screw it up. 2 times 4 is 97. See, this is one equation with one unknown. We can solve for X. So let's move the -8 to the other side. So 2X, that becomes a +8. So that'd be a +6 on that side, right? So we're going to add 8 to both sides. So divide both by 2. So X would be a +3. So it looks like our carbon is a +3. Does that make sense? 4 times, and if you do it in your head, you can go 4 times -2 is -8. So 8 plus what? -8 plus what gives me -2? Well, it have to be a +6. So 6 minus 8 is -2. And there's 2 of them to give me 6. So carbon must be a +3. So 3 plus 3 plus -2 plus -2 plus -2 plus -2 gives me -2. There you go. That's how you do it. Let's get it a little more complicated. We need to be able to assign 2 of them. We know we can assign oxygen, hydrogen, fluorine, and type 1 metals. Well, lithium is a type 1 metal, correct? It's an alkali metal. So we're going to assign lithium. We're not going to assign chromium. That's a type 2 metal, right? We're always solving for those. But oxygen I can assign as a -2. It's not bound to fluorine. It's not a peroxide. So what is chromium? Let's call it X. Let's do exactly the same thing we did there. We've got 2 lithiums at a +1 oxidation number each, right? Or you could do +1 plus +1. We've got 1 chromium. So let's call that X. So 1 times X. And we got 4 oxygens, just like this one. So 4 times -2 equals what? 0. That's a neutral compound, so the sum must equal 0. So let's isolate X. So let's move the -8 to the other side. That becomes +8. And then move that over to the other side. So it looks like it's going to be a +6 to me, right? So -8 plus 2 is -6. Move it to the other side, gives you a +6. That makes sense? 8 minus 6 minus 2 is 0. So chromium here is a +6. Now, on exams, I may ask you, for example, what's the oxidation number on the carbon? What's the oxidation number on all the metals? What's the oxidation number on every single species, every single atom? Right? So just be aware of what the question's asking. Let's do this last one. We'll call it a day. Not too bad, right? 4 elements. We should be able to assign 3. Do you see hydrogen? Oh, I do. Now, is that hydrogen bound to the metal or the non-metal? Uh-oh. Because it's in between a metal and a non-metal. Which one's it bound to? Well, this is, can you see it's an ionic compound? It's sodium hydrogen carbonate, or sodium bicarbonate. So really, if you cover up the sodium, the hydrogen's part of a polyatomic ion, the hydrogen carbonate. So the hydrogen's actually bound to a non-metal. So hydrogen's going to be a +1. It's not bound to the sodium. Sodium's a type 1 metal, just like lithium. We can assign type 1 metals, right? Easy peasy. Oxygen I can assign. It's not bound to fluorine. It's not a free element. It's not a peroxide or a free element. So oxygen's a -2. Let's solve for carbon, kind of like we did over here. Now let's see if the carbon in sodium bicarbonate is the same as the carbon in the oxalate ion. Maybe, maybe not. I don't know. Let's give it a shot. This is a long one. We got 4 species here. So we've got the sodium. 1 sodium times its positive, or sodium plus hydrogen plus carbon plus oxygen plus oxygen plus oxygen. It's up to you. Let's add the hydrogen. We got 1 hydrogen at +1. Right, there we go. We've got a carbon. 1 times X. We don't know what carbon is. We got 3 oxygens. So 3 times negative 2, running out of space, and that will equal 0, right? This is a neutral compound. Oh, I just crushed my toe. Oh, call the ambulance. Well, we know that. Let's isolate x. So that'll be 3 times negative 2 is negative 6, plus 1 is negative 5, plus 1 is negative 4. Is that correct? So x, if we move to the other side, will be a positive 4. Is that correct? So that'd be 4, 5, 6. Cancels out 3 times negative 2, negative 6. Makes sense. So x is a positive 4. So here, carbon's a positive 4. Here, carbon's a positive 3. Hey! So you'll see carbon range all the way from negatives to positives. And nitrogen ranges all around. So it just depends what it's bound to. If something's bound to really highly electronegative elements, it's going to have its electrons pulled away from it. So it's going to be a little more positive. See, it's surrounded by oxygens. They're going to be pretty positive here. If something is more electronegative than what's around it, it's going to pull electrons away from them to become more negative. Not a bad deal. So remind yourself of this concept. Review this video before we do redox later on in chapter 5, I think it is, when we do redox reactions. And we're going to use this concept when we are naming type 2 ionic compounds in the next video. Yay!